Okay. Hi, everyone. I'm Jiaxin. I'm a current graduate student at UT Austin. And today I'm going to bring the topic of how did I build the high-performance programmable NICs for multi-tenant networks. So for today's talk, the talk is really focused on answering this question. How can we build both fast and flexible SmartNICs? So the performance and the flexibility of SmartNICs are both very important. First, as we are moving to the multi-hundreds gigabits line rate, we need to build NIC that is really fast, that can catch up with this throughput. And as well, we also want the NIC hardware to be flexible and general, because we are having very fast evolving workload, like the cloud application can change in months, and we don't want to build fixed Äîsuch every time for the changing workloads. And we also want to maintain some types of the programmability of these SmartNICs. So today in my talk, I will try to introduce how we build the SmartNIC and how we design the architecture and how we use the FPGA prototype to show that we can build fast and flexible SmartNICs. And before we go into what types of SmartNICs I build, let's first go through what is a typical deployment environment of a SmartNIC. So many SmartNICs today, cloud vendor build these SmartNICs and deploy them in the multi-tenant cloud. So what is a multi-tenant cloud? So in a multi-tenant cloud, one server can co-locate multiple different tenants. And those tenants are sold to different customers. And in addition to selling those VMs, the cloud vendor are also selling those infrastructure services. For example, the network function services, their transport services, and the firewall services. And with the moving network line rate, in order to catch up with the fast network speed, to reduce CPU cycles on the host, cloud vendors start to offload these infrastructure services to the SmartNICs. So this really brings the need to build SmartNICs for the multi-tenant clouds. And in this type of scenario, these infrastructure services will be offloaded to the NIC hardware. So as the diagram shows, for example, the firewall can benefit from the the regex matching engine on the SmartNIC. And the transport can benefit from the embedded CPU cores and use them to calculate the congestion control algorithms. So once these infrastructure services are offloaded onto the SmartNIC, the tenant will still pay for a selection of these services for them when they're running on the SmartNICs. And in this talk, I'm going to discuss how should we design the NIC architecture that can efficiently offload these heterogeneous infra services on the SmartNICs in the multi-tenant cloud. So what are the requirements of running these services in a SmartNIC, and what should be the architecture requirement for a NIC? So the first requirement is offload heterogeneous. Because we have many types of infrastructure services, the SmartNIC architecture should support both fixed function accelerators and embedded CPU core offload. And because the line rate is growing very fast, there is some cases that the offload may not be able to catch up on the line rate. And in that cases, we want to avoid head-of-line blocking and avoid the overall NIC performance is influenced by that bottlenecked offload. Also, we want to enable flexible chaining, that in that case, the cloud vendor should allow each tenant to use one or more infrastructure service on the NIC by specifying their own chain of offload. So for example, here is an example, the tenant A is running a distributed file system that want to use the crypto accelerator and the decompression accelerator on the SmartNIC. And also we have another tenant B that is running secure transport offload that wants to use the crypto accelerator and also use the embedded CPU core resource on the NIC to offload part of their, to run the transport stack. And the last requirement is performance isolations. So because all these tenants are sharing the service provided by the SmartNIC should give quality of service guarantee when tenants pay for the use of the shared resources. And the isolation policy should be enforced based on the business model. And to this end, we introduce our PANIC architecture design, which is a hardware design that supports high-performance offload chaining and multi-tenant performance isolation. So there are following key components in this architecture. So first, as you can see, all the green modules are the offload engines inside PANICs. So they can be either hardware accelerators or embedded RISC-V cores. And also, we have a RMT, which is also called a reconfigurable match action pipeline, being attached inside PANIC, that the match action pipeline will parse the incoming packets header and perform match action operations. It will look up the offload chain for each tenant's traffic, as well as their isolation policies. And the center of the PANIC chip is a programmable scheduler. The programmable, which is a blue module. The blue module will enforce the per-tenant isolation policy and schedule different tenants' packets between different offload engines. And we also use a high-performance on-chip interconnect to connect all these different modules and ensures the different modules can talk with each other with high performance. And let me show a life cycle of a packets inside PANICs. So let's say a packets come in from the QSFP port. And it will first enter the RMT pipeline. In the RMT pipeline, it will look up the packet header and find what is the offload chain that this tenant is going to use. And in this case, this packet is going to use first going through the crypto engine and then going through the decompression engine. After figuring that out, PANIC will attach a packet descriptor in front of these packets. This packet descriptor contains key information such as what is the offload chain for this packet and what is the priority and scheduling policies for these packets. After that, this packet will be sent to the centralized scheduler with the packet data being put into the packet buffer and the packet descriptor sent into a centralized scheduler queue. After the centralized scheduler queue enforces the isolation policy, this packet will be directly sent to the first hop of the chain, which is a crypto engine. And after that, sent to the decompression engine, which is the second hop. And after that, directly pushed to the DMA engine, and therefore will be placed into the onto the host memory. And let's go through the components one by one. In the match action pipeline, the user will define what is the service, will configure the match action pipeline at runtime to define what is the service chain for each tenant's traffic, as well as configure the pipeline to say what is the isolation policy and priority number for each tenant's traffic. And the in the action stage of this pipeline, PANIC will generate a PANIC descriptor for every packet following a specific format. And here we show the detailed architecture of the offload engine design. So each offload engine is a self-contained component that first contains a traffic manager, which handles the communication with the switching fabric, and receive packet and send packet to the switching fabric. And it also, we have two types of offload engine. One is the hardware accelerators, which the hardware accelerators is a fixed function Äîsuch and has an AXI stream interface to receive packet from the FIFO packet queue. And we also have an embedded RISC-V core type of offload engine where we have a embedded RISC-V core can directly read packets from the per core memory, that the per core memory contains a packet received from the switching fabric. And then let me introduce the central part of the PANIC architecture, which is the programmable scheduler. So the main goal of the programmable scheduler is to enforce performance isolation. So how it does is it uses the PIFO architecture, which is a push-in first out queue, that each offload engine will have one logic PIFO inside the scheduler. So different tenants' packet descriptor will be sorted based on their packet rank and their priority inside the FACFO. So here is the example. Let's say we have the tenant 1 and tenant 2 traffic with tenant 1 has higher priority than tenant 2, and they are sharing a bottlenecked offload A. So in these cases, when the higher priority, which is tenant 1 trafficked packet enters the scheduler, its packet descriptor will be put into the front of the queue and ensures that these high priority packets will be being first served. And by changing what is the rank of the packet, and by changing the rank of the packet, it will determine how different packets are sorted, and therefore so we can support different types of isolation policies, like weighted fair queuing and rate limiting. And based on this, we allow the cloud vendor to define their own types of isolation policy based on their business models. And the last function of the programmable scheduler is dynamic chaining. So basically, we support two types of scheduling policies, like to send packets between different offload engines. So the first is the one I showed in the demo, in the previous example, is direct chaining, that packet can be directly pushed from scheduler to engine, from engine to engine. And another type is called the indirect chaining. That is, when some engine is becoming a bottleneck, hitting a bottleneck, the packet will be sent back to the scheduler and to enforce the isolation policy instead of directly put to the next hop of the chain. And we built our hardware prototype, which is a 100G FPGA prototype. So Panic currently is a standalone module that is pluggable to an open source FPGA NIC, which is called Corundum. And in our prototype, we contain the following component, like the two-stage RMT pipelines, and the interconnect. Currently, we choose the fully connected crossbar, but we also support other types of, like butterfly or other type of topology. And also, we have implemented our dual-port centralized scheduler, and we implement 3 different types of offload engine, which contains an AES, SHA, and a RISC-V core. We also implement a user space driver for Panic that allows people to use kernel bypass interface to directly interact and receive packets from Panic, as well as loading config into the Panic. And here I'm going to show a very brief hardware demo. That is talking about it contains 2 parts. First, I will show how can you configure different tenants offload chain, as well as their isolation policy and priority into Panic. And also, after loading the config into Panic, when different tenants traffic going into Panic, how Panic can ensure their traffic receives services based on the isolation policy. And the demo are using the offloading chain on the left, which we have tenant 1 is going through to offload the AES and the SHA. And we have tenant 2, which is going through a connection tracker and SHA, also the SHA offload engine. And we also have tenant 3's traffic, which is doing nothing, just bypass the SmartNIC. So in the offload chain, we can see the SHA offload engine is a current bottleneck that is shared by tenant 1 and tenant 2. And we will see how Panic shapes traffic for this bottlenecked offload in the following demo. OK, so let's start with this demo. OK, it starts. So first, currently is load the FPGA NIC kernel driver. So the FPGA NIC is currently shown as have a kernel interface that can be shown in IP link show. And now we remove the FPGA NIC's kernel driver because we want to use the high performance user space driver for Panic. And after removing that, the interface does not show here. OK, and currently we are in the driver folder, and we have a config file, which is the config in the config folder is a JSON file, And we can see this config file contains the tenant configuration as well as the NIC configuration. Like it shows the NIC PCI address, as well as the scheduling policy, which is strict priority in these cases. And it also contains some different tenants configurations. For example, it shows like the first tenant's offload chain is from 1 to 4. 1 is the ID of SHA, and 4 is ID for another. And it also shows the IP and port for that tenant. And we are moving to another tenant, like that tenant, like tenant 3, don't have any offload chain. This is fast, but OK. So right now we are moving to a next stage. We are going to load the config into Panic, as well as running the user space receive function. Yes, so currently it's loading config into Panic. And OK, and we are starting the user space receive functions. It directly print out different tenants receive throughput. And on another server, which is a Connect X6 server, we are generating throughput for different, generating packets for different tenants. So here we are generating tenant 1, tenant 2, and tenant 3 throughput. You can see the left hand shows that tenant 1, let me pause it, it's a little bit fast, yes. So we can see on the left hand side, the tenant 1 throughput is around 30 gigabits per second, and tenant 2 is 50 gigabits per second. And this is because of, in our strict priority policy, like if you see on the right hand side, tenant 1 sending rate is 30 gigabits per second, so which means tenant 1, which is a highest priority tenant, receive all the service, and the rest of the the bandwidth is allocated to tenant 2 in this example. Okay, and we are starting another example. We reduce the throughput of tenant 1, and let's see what happens. So in these cases, it is sending. Okay, and the Panic throughput change, like the still tenant 1 sending throughput and receiving throughput are the same because it's the highest priority tenant. And the rest of the band, like tenant 2 throughput increase compared to the first experiments. But yeah, it still not reached the sending rate because the offload engine is still the bottleneck. Okay, and in the last cases, like we further reduce the high priority tenant throughput and maybe also the lowest priority tenant throughput, and increase the tenant 3, which is a bypass tenant throughput. And we will see that like all these tenants can run at their full rate because nothing in the NIC is a bottleneck. And the throughput of the NIC is approaching 100G. Yes. OK, great. So this is most part of my talk. And so we have open source Panic. We have a very old version that is open sourced 4 years ago. But right now, we have a newer version with this new user space library. And we also have other ecosystem components, like we have did another work, like enhance the Panic with some smarter RSS scheme in the user space driver, help you to get better performance. So that's concludes most of my work. And I'd love to hear what people think about this, and any comments and discussion is welcome. Thank you.